So in a statistics class, you will either be looking at a population or a sample. And really, the purpose of statistics is to study samples. So a population would be everybody, and a sample is just a portion of the population. So if you're looking at the average age of people in the United States, then you would go around and you would ask every single person how old they are, and then you take the average. That is looking at the population because you're looking at everybody. Okay? And when you collect information from everybody, that information is called a parameter. I think I spelled that right. A parameter, maybe not. But a parameter is always correct. Why would a parameter always be correct? It's everybody, okay? A population could be our class. So if I gave you guys a test and I collected all the information from your test, I scored them, and I gave the average, that average is not a statistic. It's a parameter because it represents everybody. Does that make sense? Now, what are the chances that you could actually go around and ask everybody in the whole country how old they are? Not going to happen. Why? Because just during the last couple seconds, a bunch of people have died, right? And a bunch of people were born. And it's just impossible to sample everybody. So what we can do is we look at a portion of the country, and then we just collect that information, and that information is called a statistic. Okay? Is a statistic correct? Probably not. So this is not correct. Could a statistic be correct? Yeah, it might be, but probably not. So let's say I wanted to know how tall well, you guys are juniors or seniors. Sorry. Say I wanted to know how tall seniors were in this country. Okay, I can't survey all of them. I can't come up with a parameter. So what I'm going to do is I am going to sample all of you guys, find your heights, and average them, and I might get an average male height and an average female height. Would those average heights represent the parameter of the average height of all seniors in the United States? No. Would it be close? Probably. It probably would be somewhat close. I mean, it's for girls, it's probably going to be in the, what, 5'2" range. And for boys, it's probably going to be in the 5'8", 5'9" range. Yeah, 5'9". So, are we going to be off by several feet? No, if I take a sample of the girls in this class, let's say I come up with an average height of 5'4". How far off could that be from the actual parameter? Probably a few inches. Is it going to be off by 12 inches? No. So it will be pretty close. So the study of statistics, the whole point is, can we take a sample and calculate a statistic and then use that statistic to make estimations on the parameter? That's what statistics is. So we talk about probability. Is probability statistics? Not really. Okay? Statistics, the basic idea of statistics is, can you take a sample and make judgments on the parameter? Now the trouble is, your judgments are never going to be perfect. Well, there's no way to know if they're perfect. If we sample the girls in here and we get 5'4", could 5'4" be right? Yes. Will we ever know? There's no way to tell. An estimation, right. We're going to be making estimations. And sometimes it's not ethical to look at the parameter. For instance, have you ever had your blood tested? Do they take a sample of your blood or a population of your blood? The sample, right? Why is looking at the population a bad idea? You'd be dead, right? So you'll go down to the clinic and the nurse draws blood and they take that blood and they stick it in a machine and it reads it and that gives them a statistic. Is it correct? It can't be perfect because maybe that day in your arm during that second you had a little bit more salt in this arm than you did in the rest of your body, right? You ate a cheeseburger and it went straight to your arm. They're guessing. Exactly. And that's why statistics is so problematic, because a lot of people assume that statistics are truth, and they're not. They can't be. By definition, statistics cannot be truth unless it's a parameter. Now, if I'm looking at the SAGE test scores of Emory High School, will I be talking truth? Yes, because it's a parameter. We're looking at the whole population. Now, if I use our school's scores to make inferences, that's the word we use, if I infer things about the state of Utah, that would be a statistic. Do you guys see the difference? Now, we are going to treat parameters like statistics a lot in this class. And the way the book sets this up is we will be looking at situations, and a lot of times it will be a parameter, but we'll treat it like a statistic because eventually we want to be able to take a statistics and make inferences on the parameter. That is what statistics does. Okay, so for instance, the Gallup poll said Hillary Clinton was going to win the election. How do they get that information? They go around and they sample the population. Do the Gallup people talk to the entire population? No. They talk to some people. And it will surprise you how few people it actually takes. There are 335 million people in this country. How many people do you actually need to talk to come up with a good inference on a parameter? 10's probably too small. Maybe like 1,000, 1,500. That's probably enough. So, but that's a very, very, very small piece of the population, right? It doesn't actually, you don't have to have anywhere near 330 million. You don't need that much. You need a much, much smaller number. And in fact, the more people you survey, the less that your statistic actually means. And we'll get into that. But statistics is a very, it's tricky if you don't understand the purpose. So when you hear a report on the radio and it says 18% of doctors prefer this toothbrush, did they talk to all the dentists? No. So that 18% is not right, and what they don't tell you is how far off it might be. Well, you're being misled. Okay, it's very, very easy to mislead somebody using statistics. For example, let's say I wanted to take a survey on Coke and Pepsi. And I take a survey and I say at Emory High, 50% of the kids at Emory High prefer Coke and 50% prefer Pepsi. Can you believe that statistic? Well, not without knowing the information. So you ask, okay, how many people did you sample? And I say 4. I talked to 4 people, and 2 like Coke and 2 like Pepsi. Is that going to be very reliable? No. So I might say that the Coke, I got 50%, but how far off could that be? Quite a ways. If I only talked to 4 people, or what if I only talked to 2? Well, is that going to be somewhat close to the answer? Well, it can't be further off than maybe 30% or 40% off. But that's anywhere from 10% to 90%. That's a lot, right? So if I have a sample of 4, then I will show you how to complete the range, kind of. And the range might be anywhere from 10% up to 90%. How do I become more sure? I ask more people. Okay? How can I be perfectly sure? Ask everybody. Okay? But we won't be doing that in statistics because the whole point is, can we take a sample and make inferences on the parameter, on the population? So what if I ask 50 people and I end up with Coke is 45%? How reliable is that going to be? Probably pretty close. We have, what, 550 people, so that's 1 in 11. So I sampled 1 out of every 11 kids. That's not too bad. That's what would that be, 8 or 9%? Well, I'll show you that in a minute. So this might be anywhere from 40% to 55%. So I would expect that the true number to be somewhere between here. Okay? Now, in some cases, sampling lots and lots and lots of people can do you some harm. You'll see later on, there's what was it? There's a part in the book we're going to read, and it says that it had something to do with divorce. I can't remember what it was.
Did you read this book this summer?
I took a class on how to teach this class this summer. Yeah, which was really, really good. So anyway, let's say we assume that more people like Coke than like Pepsi. Okay? And let's say I'm looking at the entire country. I want to survey 1,000 people, maybe 500, 1,500 people. That's a good number. But if I sample 150 million people, so if I sample 1.5 million, and I'm asking the question, do more people like Coke than Pepsi? And I end up with Coke, we end up with 50.001. Okay? Do more people like Coke than Pepsi? Probably. Or sorry, this was 150 million, wasn't it? I sampled half of all of the people in the country, and it ended up being just slightly larger. Well, with statistics, you can say, yes, that statement is probably true. But is it really that big of a difference? No. Yeah, so well, you might as well not go beyond 2,000 or some number. It depends on what you're doing, and the cool thing about statistics is no statistician ever takes true credit for what they've done. Nobody is ever 100% sure. You can never be 100% sure when you're dealing with statistics. You can with parameters, but this is not a class called parameters, it's called statistics. So statisticians always leave a little bit of chance for them being wrong.
I'm going to write that on my test.
Yes.
So what happens when the test is wrong?
Well, this class is the class of the definite maybe. We're definitely right, maybe. Okay? Now, yes.
So, back. So, like, say with, like, the 4,
Mm-hmm.
what are, like, the chances of, like, say, the 500 people, like, the 2 you pick, like, the half that you pick?
Right. So, she brings up a really good point. So let's say I do this survey, and I run into the only 2 people in the school who like Coke, and everybody else likes Pepsi. Is that a possibility? Yes. Is it a very high possibility? No. Okay? So what statistics allows us to do is it is a very defined system that gives us sort of the chance of being right and the chance of being wrong. So we will never know for sure, and there's always a possibility. if I do this survey, then there is a formula that we'll work with that will give us something like this. Is there a chance that the true answer is only 5%? Yes, it could happen. We could talk to the only two people who like Coke, right? In which case, this range is wrong. Now, let's say that everybody goes and talks to 4 people, and everybody computes this, and everybody computes this. Will most people be right, or will this be correct for the parameter? Most of the time. So there's always that chance that we're wrong, which is why this is the class of the definite maybe. Okay? All right. So one more thing that you absolutely need to know. Okay, and I'm gonna pound that into you right now, and it's gonna show up over and over and over in this class. There's something called an observation and an experiment. Okay, an observation is different than an experiment, and this is where the news makes mistakes more often than anything. People mess up percentages all the time. They speak about percentages incorrectly, and that drives me nuts. But this is where it gets really, really dangerous. Okay? An observation is simply gathering information. So you gather info. Okay? So I can go out and sit at the park and find out the age of everybody who comes to the park. Okay? That is an observation. Okay? Now, would a statistic gathered from an observation represent the parameter very well? It depends. Okay? If I'm looking at ages of people at the park, might the age of the people at the park be skewed in some way? Is there a reason why it might not represent a parameter? Okay, what if there's a family reunion there? Yeah, not everybody goes to the park. How many 90-year-olds go to the park? 90. Not very many. How many young kids go to the park? Lots. So I would expect that my statistic would be shifted to the young side, right? So an observation, all it tells you, and I'm going to write this in red, is association. Okay, association is not causation. Causation. Okay? So if you can remember the difference between statistics and parameter, you'll do well. If you can remember the difference between an observation and an experiment, I think I spelled that wrong. Whatever. I'm a math teacher. Association is not causation. Okay? An experiment is a how would I put an experiment? An experiment is a controlled study. Okay? An experiment, if it's done correctly, will show causation. Okay? Now, you don't understand what that means at the moment. So, let's say that I go around and I sample, here's a good one. Let's say I go out and I sample how much alcohol a person drinks every day or every month. How much alcohol does a person drink every month? Okay? And I gather that information. And then I gather information on how many of those people have cirrhosis of the liver. Okay? Do you know what cirrhosis is? You get a fatty liver, and you don't have to be a drinker to get cirrhosis, but if you are a drinker, then you're more likely to get cirrhosis. Okay, so I have these two statistics, and I haven't sampled everybody, right? I'm looking, let's say, in the United States. I have a list of people, how much they drink a month, and whether or not they have cirrhosis of the liver. If I start to notice that the people who drink more tend to have cirrhosis of the liver more, can I say that alcohol causes cirrhosis of the liver? No. That is an association.
You say and
So I, right. So I go over here and I look observation. Did I create a controlled study where I gave people alcohol and measured their liver? No. That would be an experiment. When you force people to do specific things and then you measure it, that's an experiment. Now, is it ethical to perform that kind of experiment? Not on people, right? Do we do those sorts of experiments on animals? All the time. Okay?
What's the matter when my tattoo says it's not?
Well, some, yeah, some people, yeah, you're gonna get a brain tumor. Sorry, quit washing your hair. So, you have to be very, 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 very careful with observations. Now, does the medical community believe that alcohol causes cirrhosis of the liver? Yes. Have they done experiments on animals? Probably. I'm not sure. But if you just go out and you pick a set of people and you ask them questions, you are doing an observation, and you can never say that it's causation. You cannot say that alcohol causes cirrhosis of the liver if all you have done is an observation. Okay? There might be something else at work. For instance, let's say there's a gene, and I'm making this up, let's say there's a gene that makes you more likely to drink alcohol. Okay? And that same gene also makes you more likely to get cirrhosis of the liver. It could be the gene that's causing the alcohol consumption and the liver damage, and the alcohol and liver damage just happens to be a coincidence. And we're going to look at a lot of these at one point. Yeah. So when you read a news article or you hear something on the news that cell phones cause brain tumors, okay, you have to be very careful. Did they do an experiment? Probably not. Right? Because they're not going to do something that might cause a brain tumor. That's unethical. So just because there's an association does not mean that one causes another. Okay? A really famous one is back in New England, when our country was first created. If you graph the number of churches in New England versus the number of bars in New England, the graph looks like this. So what that's saying is, as more churches were added in New England, the number of bars that were added went perfectly in line with it. Okay? So, does building churches cause more bars to be built? In Darian's world, yes. No.
Well, because if you're building more churches, that means there's more people.
Right.
Building more people for.
So the actual answer is the population increased. Right? As the number of people increased, there were more churches. Actually, oh, I drew this wrong. This should be a straight line. I'm sorry.
Yeah.
Sorry, there we go. So, churches do not cause bars. Right? That's an association. It's not causation. So, can you do an experiment to see if churches cause bars? You might be able to come up with something and make people go to church and see if they go to bars more often or something like that, right? But if all you do is go out there and gather information, you cannot say one thing causes another, even if it seems overwhelmingly true. Okay? Association is not causation. Okay, so I want to show you one of my favorite cartoons that I found. Oh, I don't remember when. Um, uh-oh. Okay, look at this comic. I found this a couple years ago, and I just laughed, and until today, you wouldn't have understood this. Okay? So the boy says, I used to think correlation, which is an association, a correlation implied causation. So the boy is saying, I used to think that if two things were associated or correlated, that meant that one thing caused another. We just learned that's not true. Then I took a statistics class. Now I don't believe that anymore. So the girl says, sounds like the class helped. And he says, well, maybe. Do you get it? Can he say that the class caused him to change his mind? Well, it did, right? But he's not allowed to say that because he took the class and he knows the rules. Okay? So it's kind of, we're stuck. Right? By defining association and causation and correlation the way that we have, we can't really be sure that one thing caused another even when it's obvious that it does. So you have to be very careful with how you use statistics. Yeah, what else could it have been? I don't know. And maybe you consider this an experiment. I guess technically that could be an experiment. If you take this group of people and they think that correlation and causation are the same thing, you put them in a statistics class, and then you ask them later, and you'll see, oh yeah, it went up. Then, yeah. But anyway, it's kind of a funny joke. Yeah. Okay, so I'm going to stop the video, and we're going to read chapter 1.